Good morning, everybody. So last time in last class, I have discussed about the heat transfer. What are the different mode of heat transfer like conduction, convection, and radiation, if you can recall. That we have discussed. Now today we will we will learn about the heat transfer equation or a heat transfer through a wall. Say for example, in this room, if the heat is very high, then if we close it, then heat transfer will be very less. If you open the door, then heat transfer will be very high, and immediately it will be get cold. Now, in the closed condition, the heat is transferring from through the wall. At what rate? That thing mathematically we can calculate. Or in vice versa, in a cold storage, say temperature is 4 degrees centigrade, outside temperature is say 40 degrees centigrade, then at what rate that this heat will enter from outside to inside, that also we can calculate, which will actually help us to know the capacity of refrigeration we need to install in that cold storage system. Now to start to derive that mathematical equation or understand the mathematical equation and use of that mathematical equation for solving the practical problem, we should understand how a heat can transfer from one place to another place. What are the different bindings or resistance of this heat uh, to transfer from hot condition, say T2, which is higher temperature, to T1, towards the T1. Say in this side it is higher temperature and heat is flowing from this side to that side, and this side to that side. So first resistance it will experience that is resistance in the hot wall and resistance in cold wall, and another resistance through the wall itself. So through the wall, this is known as the conductive heat transfer. In this through the wall, when it will experience certain resistance, or in reverse of that conduction, that is the conductivity. So that conductivity, and also if we see the heat transfer phenomena through the pipeline, then we will understand from inside the pipe, say heat is transferring towards outside, because outside temperature is lower, inside temperature is higher. So it will also face the same your resistance, or rather the conductance, the conductivity through the wall of the tube, and the interface of the wall and liquid, or the interface of the outside air to wall of this tube. So this, if we uh, try to understand the mathematics of this, or the dependable factor of this heat transfer, then Fourier's first has shown us the road, that is Fourier, that is known as Fourier's law. This law tells us that heat flux, this is how much heat will be transferred per unit area per unit time from hot body towards the cold body, that is directly proportional to the del T, that is the temperature difference across the wall, and this proportional constant is K, which is thermal conductivity, where the Q is the heat transfer rate, that is how much heat will transfer per unit area, here per unit area, the weight watt per meter square. Now this is the thermal conductivity, which depends upon the all the x, y, z, and del T also in a circular or three-dimensional system. Now if you want to derive this equation or simplify this equation, or adding this conductivity towards the from one side to the wall, another through the wall, and from from wall to this side, then we will see this is the coefficient will be there, that is H2 and H1, that is the heat transfer coefficient, and through the wall it will be conductive heat transfer. And if we add it, then we will get one overall heat transfer coefficient. This overall heat transfer coefficient, which will depends upon the resistance. This is the resistance, first resistance, second resistance, third resistance. If we add these three resistance, then total resistance we will get. And as we know, the conductivity is just reverse of this resistance. Then overall heat transfer coefficient, that will be the 1 by adding all these things. So this Q, which is the heat transfer rate, that is the overall heat transfer coefficient multiplied by area and heat difference of heat temperature across the wall. Then if you know the overall heat transfer coefficient, that is the conductivity and heat transfer coefficient from both sides of the wall and area of that wall and temperature gradient, then we can easily calculate the amount of heat transferring across the wall. And in vice versa, if we know this Q and overall heat transfer coefficient and del T, then area easily we can calculate through this. In a similar way, we can also calculate the heat transfer across the wall of a tube, where the difference will be area, because here area is the 2 pi r L, that is total area, that that will be little bit different. So in this case, del T also we can take as a logarithm difference of this del T, because we can't get the direct whether it is co-current or counter current. All these are dependable factor. So in that case, overall heat transfer coefficient you will get from this equation, that is 1 by U E equal to the summation of all this resistance, because overall resistance will be the summation of the resistance of wall side, hot side and cold side and through the wall. Then similarly, if we get the value of U and del T and Q, we can get the area requirement, or in other way, if we get the three value, then we can easily calculate the Q. This in this slide we will try to understand the problem, what types of problem we need to solve, that we can understand the T out, that is one of the example temperature. So better we will do this problem in our class itself in presence of you people. So you try here how to solve this problem, and try to solve it outside the class. So inside the class we will again discuss it. If we get any difficulties, then we will discuss in the class itself. Thank you for your patience hearing and to watch this video. Thanks all.